just that the last big thing lasts a little bit. So here we go. I am so excited. I can't even tell you.
You just did.
I can't tell you how excited I am, though. Like
32.
There's a date and a time, and the time
Yes.
is 30 minutes ago. You can't see it anymore.
Oh, we about to run impedance?
Oh, God.
no.
Dang it.
Sorry. Good try. Inductors. You right? Are you excited? Okay. So I have to tell you that prior to like reading this stuff over again, I mean, I did this a long time ago. But this is brand new stuff for me to teach. I've never taught this stuff before. You guys are my guinea pigs. And I was like, oh, inductors, that sounds scary. And then I was reading, I'm like, really? Not. Like, really, they're less exciting than many other things. Let me tell you what an inductor is. An inductor is an element that you can put on a circuit. What else can you put in a circuit?
Resistor.
You can put a resistor in a circuit. Yeah, what else? A capacitor. What else can you put?
Light bulbs.
A light bulb or a battery. And then the other thing that you can put in, the other thing that we're talking about putting in is an inductor.
Or a switch. We forgot the switch.
Oh, well, you didn't say it earlier. Or a switch.
Transistor, a diode.
We're not going there. These are all wonderful things, but they're not things that are they are
Circuit.
beyond the scope of this course.
Okay, let's try that.
The last thing we need to put in a circuit is an inductor. Okay? So let's back up for just a second. What is a resistor? Like, what's a resistor made of?
Carbon film.
Could be carbon. Doesn't have to be. What else could it be made of? Metal. It's just a piece of wire or metal with a certain resistivity, right? Like a certain diameter and a certain length and a certain material. And as a result, it's going to resist the flow of electrons, right? Does that make sense? No big deal. That's really all it is. What's a switch?
But with the closed circuit, it's just wire also.
It's just a wire, right? It's just a wire with a break, and then you get connected, and then life is good, right? What is a capacitor?
Two metal plates.
Metal plates.
Metal plates like this, right? And those two metal plates can do pretty cool stuff, because what do you do in between the two metal plates? What do you establish?
Electric field.
An electric field, right? And that electric field does what? Why do we use capacitors?
Store energy.
Yeah, we're storing charge, which stores electrical energy. Does that make sense? And we can use it later. So an inductor does a similar thing. An inductor is not a big, scary thing. An inductor really is just a coil of wire. That is all it is. So you have a coil of wire. Whee! Okay? The current's going to go through the coil of wire. That's fun. The kind of neat thing, though, is that when a current goes through that coil of wire, what's established in that coil then? Yeah.
Oh.
But nothing scary is happening. So I really want to make that clear. It's just like a straight wire, right? It's the same, like all we're doing is making it a little curlicue. That's it. Okay? A perfect inductor, an ideal inductor, has zero resistance. Okay? So it's just a piece of wire that instead of being in a straight line is now in a loop. And as a result, we can we establish a magnetic field because it's like a little tiny solenoid. Okay? So with a current flowing through, that I generates a magnetic field. And hopefully that's not a scary thing. Now, Jack, you said a minute ago that when electricity and magnetism came together, that's what everything went something for you. Is that an okay statement, or do you want me to back up and make sure that's okay?
That's fine.
Okay, that's not a big deal, right? Like current going through, magnetic field, and okay. Now, if the current's constant, life is not super exciting. But when the current changes, when there's a change in the current, that means that there is a change in the magnetic field. And if there's a change in the magnetic field, we can say that there's a change in the magnetic flux through that loop. Does that make sense? Because that coil of wire is a loop. And so the changing current results in a changing magnetic field, which results in a changing flux. And what happens when you have a loop of wire and the flux changes?
Current. No. Force.
What happens? What's that? It does. It creates, or the fancy word for that is induces a current. So by having that change in flux, because you have a change in current, that changes the flux, and that induces, there should be a U in there, it induces a current in the coil. Okay?
So it resists change.
It wants to avoid any change. It wants to undo any change. So this is really just Faraday's law. We're just doing this. We're just talking about the exact same thing. It's like we're just a repeat day.
So like the current opposes the change.
The current opposes the change. Yeah, and we'll talk about what that means depending on how it's going up or down in just a second. Okay. Now, I mentioned that inductors they've got some similarities to capacitors, and one of the things that they have in similar, I'm going to have you make a little chart at the end today to kind of compare the two, but one of the things that's interesting about inductors is that they have something that we can describe them by. Capacitors have capacitance, inductors have?
Inductance.
You got it. Yeah, it's not that scary, right? And the inductance is something that we can use to describe how large or small that inductor is. Okay? Inductance, for some logical reason to someone, is marked with the letter L. I don't know why. If I did, I would tell you, but I didn't take time to look it up. I'm sure somebody could find it out for us. Okay? And the inductance is defined as the magnetic flux divided by the current. It's the flux to current ratio. I was going to print out a nice little sheet for you, and I ran out of time. You know what? I think I'm going to have you start making our little chart of conductors and inductors kind of comparison chart right now. You could do this on a separate piece of paper. If you would like to do it on a plain piece of paper, you can grab a piece of scratch paper if that makes you happy. Whatever works for you. I know different people are different, so we're just going to make ourselves a little chart here to compare capacitors and inductors. Okay. Capacitors are defined by their capacitance, and perhaps you remember that C is equal to Q over V. It's the charge to voltage ratio. Inductors are defined by their inductance, L, which again is the flux to current ratio.
Wasn't capacitance also epsilon naught?
Yeah, and we're going to get there. Yes, we're going to get there in just a second. Hold on to that. Oops. Okay, now I'm going to go back to the original story. I just wanted to start our chart because I feel like charts are helpful for me. I don't know if you find them helpful, but I do. Inductance is measured in, also named after a famous physicist, not one that I knew a lot about or know a lot about. Henry's. Yeah, named after a guy named Joseph Henry. So inductance is measured in Henry's. Marked with the letter H, capital H. 1 Henry, that is the SI unit of inductance, is defined as 1 Weber per amp. I don't know why Weber is such a funny name, but apparently it is to you.
Units named after people.
Yeah, there isn't one called the Shumway, though, so, you know,
Yeah.
You can
just
make
saying.
one.
You just pick some random things and put them together. And just to remind yourself of Weber, they all are really, yeah. It's a Tesla. And there's that guy meter squared, right? Love him. So that's just to give you a sense of what a Henry is. Do you remember what capacitance was measured in? Farads, named after,
Faraday.
not Farad, Faraday. Yes. Yeah. But if you remember when we started talking about capacitors, we said that a farad is like a ridiculous thing. And so when you're talking about capacitors, you're usually talking about microfarads or millifarads, things like that. Same thing with Henrys. Generally, we talk about microhenries or millihenries. Okay, those are the orders on which we usually are talking about these little inductors. Okay.
So Henry though is like the one name, like the one unit that actually really sounds like a name. And I'm just imagining little people like
Microhenries.
that.
Yeah, yeah. It's true. I have a little cousin named Henry, and I'm like, there he goes. Yeah, it's true. I don't think I could probably ever name a kid Henry.
Not anymore.
Not after having known that, you know, a long time. Yeah, yeah. I don't know a lot of physicists with kids named Henry. Maybe there are, and it's not around me. All right. So
Maybe you're friends with the wrong physicist.
maybe that is entirely possible. So Gabe was excited about defining capacitance in another way based on the physical parameters. So we can say defined physically. Do we remember what that equation was?
Whatever, the P-looking thing.
Not P-looking thing, that's rho.
It's epsilon, not A over D.
Yeah.
Oh wait, I'm thinking.
Okay.
We should make a list of equations that aren't on the equation sheet.
right.
Okay, you should do that. That sounds like a good plan.
I think I would do that.
You should share it.
I
He might.
shared your spreadsheet.
We'll see.
Yeah, better.
All right. We can also define inductance in terms of physical parameters. Let's start with the idea that we're making a magnetic field. We know that a magnetic field through a solenoid is defined as mu naught Ni over L. Does that look familiar to you from before spring break at least? I think. Didn't we do that before spring break?
Yeah.
What does that mean?
That's the magnetic field that's generated inside a solenoid with a current going through it.
Oh, it was a while ago. Sure. Okay, I'll go with it.
Does that sound okay?
It's script L.
Yeah.
L.
Yeah.
What's the difference here?
Capital L is inductance. Script L is like.
Oh, yeah, okay.
This one you should know. What's that?
Line, maybe,
No, that's not a line integral.
maybe,
If it's a
maybe.
What?
It is a dump.
AB? Yeah, because it's what?
Dump.
This is flux, right? Yes. I don't know what. Woo! Welcome to magnetic flux, yes?
That's right.
Yes.
AB.
I wrote it up here earlier. Right there. And right there, yes? Are we okay? Okay. I know we're getting close, but we have to remember this stuff. So magnetic flux, what letter is that?
It's a phi capital.
It's a capital phi. Yeah, it's up there. Fourth from the end. Okay. Magnetic flux is defined as AB. So the area of what?
The field going through.
The area of the loop, right? Times B, which is the magnetic field. So, well, we can just multiply A by this mess. Mu naught times Ni over L. Okay? Except, I did skip one thing. This is the magnetic field in a coil. Hold on just a second. Da-da-da-da. And I need to talk about all of the turns. We need to talk about all the turns here, so there needs to be a squared in there. So let me add in something here to make that make more sense.
Why is it squared?
I'm getting there.
Okay.
Hold on. So the flux is equal to the number of turns times the flux per turn. Okay. That's just the definition of what it is. Yes, no?
Yeah.
Yeah?
Because magnetic field is going through a bunch of turns.
Right. Lots of turns. Exactly. So the flux is going through each of those turns. So the total magnetic flux is going to be the number of turns times the flux per turn. And the B field is generated in that solenoid. That's where that N comes from. So that's where the two N's are. So that's why it's N squared. Is that okay with everybody? Yes or no? Talk to me.
Where do both ends come from? One more time.
One N comes from here,
Right.
from the magnetic field that was created, right? So you have a solenoid, magnetic field is created. There's a magnetic field. Now if I'm talking about the flux through a bunch of turns, then I need to know the flux through one turn. And then I'm going to add up all those turns. So it's kind of weird because before, when we were just talking about a solenoid, we weren't talking about inducing anything, so we didn't care about the flux. All we cared about was that we were generating a magnetic field, right? Generating a magnetic field inside a solenoid. Is that okay?
Wouldn't the flux per turn not have an N? It's just one turn.
No. Okay. Okay. Let me back up. Solenoid creates magnetic field, yes? Do you guys agree with that? Okay. And so that magnetic field exists. So here's my solenoid. There's a magnetic field that is created by it. Okay? The weird thing with an inductor is that then we're going to take that flux that is created there and we're going to change it. And that's going to induce a current in the same coil that had the current going in it before. Do you understand what I'm saying? You want me to say that again?
Say it one more time.
Okay. Well, I'm going to back up for just a minute. I'm going to back up to last week. Last week, we talked about a current being induced, yes? Or maybe it was 2 weeks ago, it was when your teeth were being extracted.
Last week.
Okay. So we had a loop of wire. Does this look familiar to you? Yes, this was our loop of wire that we were playing with. We had the magnetic field that was going through it. Okay? Magnetic field, let's say it was going this way, this way, this way. Yes? Okay? And then it got stronger. The magnetic field that got stronger created a current in this loop. Does that sound familiar? Okay? And how did we figure out what the current in this loop was?
The magnetic field creates against
The magnetic field goes against the one that was happening, right? So it's getting stronger in this direction, it's going to create a magnetic field like this, and that's where that current's going to come from. Is that okay? Okay. Now, let's say that there were 3 of these that were looped together. Does that make sense that then the change in flux is going to be different because there are more loops? Okay? That's where that second N comes from. That the total flux is this loop plus this loop plus this loop. That's the total flux through this system. Is that okay?
So you use the total magnetic field for each ring. Okay.
Right. Because the magnetic field goes up with more loops, and the flux goes up with more loops.
Okay.
Is that a little bit better? Brian, how you doing? Doing okay? Do you need to go to the bathroom?
No.
Okay. If you do, go ahead. Just, you don't need to ask, just go. Okay. So that's where this N comes from, that's where this N comes from, which is why we've got N squared. Life okay? Okay. So, let me erase that. And then we're going to just make a big mess with this because, well, we can. So, if this is your flux, and inductance is flux per Oops, not per L, per I.
Divided by I.
Well, then we can put stuff together, right? So we can put this big nasty mess, mu naught n squared I over L, divided by an I. Oh wait, there's an A in there too. Forgot that A. I's are going to go away. And now we can describe the inductance of the inductor, the coil of wire, that's all it is, as mu naught n squared A over L. Mu naught is a constant. N is a physical parameter. A is a physical parameter. L is a physical parameter. Is that okay? So in the same way that we did with the capacitors, we've got a new definition for L that we can also use to describe inductance based on the shape and size of the inductor.
Wait, small question. For capacitor, for D was the
Distance between the plates.
Okay, yeah.
Mhm, yep.
What is the L again?
L is the length of the solenoid.
Okay, this is about the number. Would be the length of the wire in the
Nope,
loops,
it's-
or all the loops combined?
Yep, the loops combined. Yep, yep. A times L, if you think about it, the area times the loops gives you the volume of the solenoid. Does that make sense?
Yep.
Yeah. Okay. Life is okay so far? I really hope I'm not hosing you over. I hope this is kind of sitting okay. It's a lot of information. I totally get that, but I want to make sure that you're doing okay with it. Yeah? Okay. So I have an example from the book. I'm just going to read it to you because I didn't get a chance to type it up. So listen carefully. I'll read it to you twice. This stuff.
What number?
This is 3212 or 3312. Oops. It says, an inductor is made by tightly wrapping 0.30 millimeter diameter wire around a 4.0 millimeter diameter cylinder. What length cylinder has an inductance of 10 microhenries? An inductor is made by tightly wrapping 0.30 millimeter diameter wire around a 4.0 millimeter diameter cylinder. Okay. We want to know the length of the cylinder that has an inductance of 10 microhenries. So you need to know the diameter of the wire because that's going to help you to figure out the L, right? Because the length of the cylinder, so they're tightly wrapped, which means that each wire is going to be right next to another wire, and the total length is going to be equal to the number of wraps times the diameter of the wire. Does that make sense? Okay. That didn't seem completely obvious to me at the beginning. That's why I wanted to make sure you got that. So just to kind of go through some of this, and I know you guys are still working, some of you, and that's okay too. I'm just going to kind of walk it through too because it's good to do. So L is mu naught n squared A over L, little l, right?
Little l is the number of turns divided by the diameter of the wire.
Little l is the number of turns
Times.
the diameter. Yes. So you can either write it, like you can either write L in terms of N, or you can write N in terms of L. I'm going to write N in terms of L, I think. But I don't think it really, I mean, I think you can go either way. So N is going to be L over the diameter of the wire.
Yeah.
A over L. So one of those L's cancels, doesn't it? So mu naught L A over diameter of the wire squared. Is that okay? And then if we solve that for little l, then it looks like that's going to be, so what, L diameter of the wire squared over
I don't know my calculator.
mu naught A. You could borrow a calculator if you need to.
-70.
Sure what happened. I'm pretty sure it's like 90.
How's it going? Is it, you have a big smile on your face as though maybe it's...
I think it might actually be right.
Oh, okay.
It's a decent number.
What?
You got 190, so that's
100.
not like
190 what?
turns.
Oh,
Oh wait, length.
I want to know the length.
Wait, the
Isn't it,
length.
is it, it's,
Yeah. Okay. And then the
5.7.
length. Oh, yeah, that's right.
Yeah.
So
Is that what you got?
Yeah.
Oh,
I
whatever.
went, yeah, I went through a few more steps in this, but.
Oh,
That's okay.
how close the diameter of the wire is? Okay. Yeah, I got it something.
I got 5.
I got .05.
Oh, 5.7?
Oh,
Is that what you got?
5.6.
I got .057 meters.
Right, look at my units. What are your units?
Yeah.
How do the units compare? Are we
I
okay?
got 100 meters.
You're wrong.
My first answer was like something like 18.
What did you get, Logan?
It was like 5.7 times 10 to the 11.
What did you use for mu naught? Did you listen to AJ? Did he tell you that it was 10 to the 7th?
No, I did 10 to the negative 7.
Did you do Henry's times 10 to the negative 6?
I did.
Did you do millimeters?
And did you convert all your millimeters? I'm guessing that there's just a conversion that
Yeah,
got messed up.
this week I'm doing something.
Did you divide your diameter by 2 when you were finding the area?
I got that.
Are you sure you use the radius and use millimeters?
There are a lot of places that are like really like little places you can mess up on this, right? Stink.
There's so many unit conversions. What is that called? What is the terminology for unit?
Square that.
Dimensional analysis.
Dimensional analysis. A lot of dimensional
Square. A lot of
Oh. Dimension.
the dimensional analysis works out.
How are we doing, friends? Are we doing okay? Logan's got some hundreds and thousands.
Yeah.
Some zeros he's dealing with. Besides that, can we go on? Okay. All right. So, here's the thing about an inductor. If you have a circuit, like let's say with a battery,
Let's just say,
for example,
as opposed to an AC power source.
and an inductor,
Is this notes or not?
this is, yes, I mean it's notes, okay? Talk to me about the current in this circuit. It's constant, right? What is an inductor? It's a wire, right? That's just put into a loop or to a coil. So it's nothing, there's no magic that's happening. I want to make that really clear. Yeah.
I'll ask later.
Okay. So tell me about the current in this circuit.
Constant.
It's constant. It's not very interesting, right? If you have constant current going through a loop of wire, like, is that interesting? Is it going to do anything fun? It's going to heat the wire up, sure, yeah. Maybe I put another resistor on there so that it's not going to heat the wire up too much. Is that interesting?
No.
No! Inductors are not interesting if the current is constant, okay? If I is constant, then inductors are boring. Inductors, like, they don't do anything. They're just sitting there. Now, is there a magnetic field that's established? Yeah. But it's just, I mean, it's just because there's a coil of wire. Like, whatever, right? It's not a big deal. The inductors, I'm going to say, are not very exciting. Not too exciting. Boring. Okay? If R...
Would that be on the AP exam? There's no constant. Please describe the inductors.
Boring. Yeah, no, I didn't get to write that question. If the resistance of an inductor is 0, then tell me about the potential difference across an inductor. Also 0, right? V equals IR. Doesn't matter what I is. If R is 0, V's got to be 0. Boring. Okay? It's much more exciting when what?
There is a change in current.
Yeah, when there's a change in current. We like having a change in current. That's when life gets more fun. Okay? If I have an inductor...
Wait, inductors do have resistance though, right?
An ideal inductor does not. So we're going to talk about ideal inductors. When you do electrical engineering, right, then you're going to have to acknowledge the fact that inductors do have a little bit of resistance. But if you have an inductor in a... So from a theoretical perspective, they do not. Now, if you just have an inductor in a circuit with a power supply, then there will be some
What about internal
resistance.
Then
Well,
if there's internal resistance.
right. Well, yeah. I mean, so but it's going to heat up, right? And that heat comes from the resistance. But the resistance is going to be so small that any other resistor that's on there is going to make the resistance of the inductor virtually 0. Does that make sense?
Because I was playing with electromagnets.
Of course you were.
And no, but they measured resistance of like 80 ohms. Does that mean they're just wrapped 1.5 zillion times?
Perhaps.
Okay.
I mean, because it's the same deal when we were dealing with just a simple circuit with a resistor. We assumed that the wire has 0 resistance, right? But technically, wire does have resistance. It's just that it's so little compared to the resistance of the resistors. Does that make sense? Okay. When current changes, though, life gets exciting. We've talked about this a little bit, but let's kind of unpack it a little bit more. So when the current increases, so maybe we have a variable power supply and we turn it up, right? Or maybe a switch, maybe there's a switch up here, and we close the switch. When we close the switch, that would imply that we've got current that's increasing, right? So if you are increasing the current, well, we know that that's going to increase the magnetic flux, and it's going to induce a current in the inductor. Okay? In what direction?
Opposite current.
In the direction opposite the current, yes. Okay?
Why?
Faraday's law, Lenz's law, right? I mean, it's because of Lenz's law.
So if 110 The
Lenz,
intense
okay,
independent
does that make
law
sense?
that-
Is that, I'm not trying to be curt about it. Like, does that make sense to you or no?
It doesn't.
Things have no advantageous law in the current environment.
Okay, so we have to go back to Faraday's law.
Okay.
So Faraday says, oh, there he is. Faraday says that if you have a change in flux,
Oh, there's a negative sign.
that negative sign is Lenz's law. Oh, right there, boom, describes the direction of the induced current. And the induced current is always going to be opposite. It's going to try and undo the change.
Got it.
Is that okay?
Yes.
Okay. Okay. What if the current decreases? What happens to the magnetic flux then?
Decrease.
It goes down. What's going to happen inside the inductor then?
Well, it's going to go in the direction.
It's going to induce a current in the inductor
Same
in the same direction, right? Okay? So depending on what's happening, it has nothing to do with the value of the current, the magnitude of the current. It has to do with the change of the current. I feel a derivative coming on here, right? The change in current affects the direction of the induced current. Look like you have a question.
Okay, so I got the first part, and then I just think, okay, wait, so I understand the first part. So if current increases, then magnetic flux increases because and then, one second, I just have to think about this. The opposite direction, but like in the,
It's getting weaker, so it won't
oh, in the same, oh wait, no, I think I got it. Yeah, in the same direction because the current's going down. Yeah, okay, that makes sense, yeah.
Are you sure?
Yeah.
Okay.
Sorry, because I was,
No, it's all good. I would rather you ask questions, even if they're PC questions, than to not ask questions at all. So it wants to undo the change, right? That's all it's trying to do. It doesn't like that change. It doesn't like that change, so it's trying to undo the change. Okay? In doing so, Faraday says, oh my gosh, well, by inducing that current, we are now establishing,
Ms. Carver,
what's up?
why would you need to have an inductor for that to happen?
What do you mean?
Like, isn't that just merely a wire?
Hold on just a second. No is the short answer, but let me write something down first. Is that okay? Actually, no, I'm going to answer your question first. You only have an induced current in one specific case. If you just have a wire and I change the current in the wire, is that going to induce a current in that wire and anything? Do you understand what I'm asking?
There's no loop.
There's no what? Loop. So if there's no loop, there's no area, so there's no flux.
Well, yeah, but like if you have like a circuit, I mean, technically you consider that a loop. But like,
But the magnetic field isn't going through the loop. Does that make sense? You have to have that area. Yeah.
So, like, Nathan, sometimes you can end up with unintentional inductance, but usually it's just because the way you wired it, and it's always so small you don't. Like, if you wrap the wire in like 3 loops to make it shorter so it'll fit, then you haven't made an inductor
Unintentionally.
unintentionally.
Yeah. Okay. So unlike this situation here where I is constant and there was no potential difference, as soon as we have an induced current, Faraday says we have an induced EMF, right? Faraday says that induced EMF is equal to D, we should write this down the right way. So what?
so aggressive.
Right? I'm going to put absolute value signs around that because I'm not going to worry about the negative sign. We'll worry about the direction in a minute. Okay? Faraday says, this is Faraday's law, right? Faraday says that whenever you have a change in flux, you have an induced EMF. So now, instead of having a delta V that is 0, we have a delta V that does not equal 0 across your inductor. Now, that's interesting. That's different.
So now it has a resistance.
No.
No.
We don't call it an induced resistance. It's inducing a current. And as a result, there is a potential difference across it.
And it has a
It does not have a resistance. We're not taking it that step.
But it has an impedance. AC circuits.
Stop. All right.
That's
d phi dt we can also write as L times di dt, because phi is just equal to L times I. Okay? Is that an okay statement? You want me to go back and talk that through again? L was defined as phi over I here.
Read the number of turns.
It's, let me put an M. There's an M here, so that's the total. Yeah. And that the L, the big L, takes into account the number of turns as well. Okay? In terms of a sign, we need to be able to describe it in terms of, like, is it a positive potential difference or a negative potential difference? And we're going to do that in the same way that we do with a resistor. So looking at a resistor, if we have just a simple circuit with a battery and a resistor, you know that the total potential difference around the circuit has to be 0. We call this positive potential difference. And so then across the resistor, in the direction of flow of the current, so let's say that the current is going this way. I'm just trying to make that a smaller picture here. Okay? Delta V is equal to negative IR. We've got a higher potential here than we do here. That's the way that we defined a resistor ages ago. We may not have explicitly said that, but we implied it, I guess. For an inductor, you do the same kind of deal. So that's how you draw an inductor, right? It's just a little curly Q. If the current is going this way, we're going to say that we have a positive potential at the top and a negative potential at the bottom in the direction of the current flow, which means that delta V is equal to negative L di dt. So again, there's only a potential difference if there's a change in current, and it's going to go opposite the change.
That current that you just wrote is the current.
That's the initial current. The initial current, not the induced current. So let me take it that next step that I think you're kind of getting at, Jack. If the current increases, that is to say that di dt is greater than 0, the potential difference across the inductor is less than 0. So, as you were kind of implying, it's acting, I don't want to say it's acting like a resistor, but it has the same effect in terms of the potential difference. If I decreases, again, that is to say that di dt is less than 0, then the potential difference across the inductor is greater than 0. Is that okay? When I was reading through this the last few days, the thing that I had to keep reminding myself, and the thing that's really, really important, is that the potential difference that is established across an inductor has very little to do with it has nothing to do with the current itself. It has to do with the change in current. Okay? Doesn't have to do with the magnitude of the current. It's all about the change. So it can be a little tiny current, but if it changes really fast, that's what matters. Okay. My guess, and I don't know the answer to this question, how many of you have taken some sort of car maintenance class or have any idea how a car works? That's what I thought, because I don't either really. I kind of wish that I had. Like, I kind of feel like I should know. Have you heard of a spark plug before?
Yeah.
Yeah. Logan, what's a spark plug?
I don't know.
Heard of it?
Nailed it.
I've heard of it, and you put it in.
It starts the engine.
It's the what?
It starts the engine.
It starts the engine. Okay, so let's. This is Carbling's version of Car Information 101. I know that when you turn when you're starting the engine, right? How does the car work? You put gas in and it goes, right? Okay? There has to be some sort of ignition. Oh, that's why they call that thing the ignition, right? And the reason that all works is that there has to be a little spark, a little something that happens. And here's the nice physics secret, is that it comes from an inductor.
And that's the only use inductors have.
No, actually, we're going to talk in just a minute. Without inductors, we would be living in what you guys would probably consider like the dark ages. There would be no communication. There would be no radio. There would be, you could speak vocally, but you couldn't record and right. Exactly. Because there are inductors in your ears. Whoa,
In
no.
your nose.
But no, seriously, honestly, all electronics use inductors, and without those, we wouldn't have any of that stuff. Okay, so we'll get there in just a minute. But I do want to let you know, because the spark plug thing is kind of interesting, and it's kind of relevant in that that's the way that we get a lot of spark things. So if we have, Teresa was really excited about putting a switch in.
This is the spark plug.
What's that?
This is the spark plug.
This is the spark plug. Yes. So there's the switch, okay? And there's the inductor, and everything is fine. The switch is closed. There's current running. Life is good. Nothing exciting happens. As soon as you open that switch, what happens?
DIDT.
DIDT happens, right? DIDT happens really, really fast. So DIDT is really, really, really big.
And negative.
And negative. And as a result, right in between those two spaces, because there's a lot of energy there, okay? That's where the spark happens. And that's what lights the gasoline.
No.
I'm sorry, say that one more time.
Way.
The whole tank just ignites.
Say that one more
No.
time. That kind of the whole.
Okay, so when it's closed, there's current running, life is good, right? That switch opens really fast, and when it opens, the IDT changes, or I changes really fast, so the IDT is really, really, really big. Does that make sense? And that, because that current happens so fast, the potential difference is so big, that large potential difference creates a spark in that space.
So potential difference across the inductor, right? So why does the spark happen?
Because that it's greater than the breakdown voltage of the air between in the switch.
Okay.
Yeah.
So it's created by the inductor.
Right. Yes. Yeah. If you just had a wire, it wouldn't do that. Right. That potential difference has to happen because there's an inductor there, because there's a change in current.
You can do that with like a really powerful battery there, right? Just a wire, a huge battery.
It has to be a solenoid. It has to be an inductor.
But I'm saying if the voltage was the battery voltage was big enough,
Then you could just move the
What is
wires
that air
back
spark?
and forth.
across the wire.
Yes, but that's not because of this.
Yeah. But
It's you. So this is not the only way to get a spark, right? Yeah, yeah. You can also wear your wool socks and do that whole thing too, right? Like there are lots of ways to get sparks. This is just one, and this is the way that your car uses to do it. All right, let's do a problem quick. Again, I don't have it typed up, so I'm going to read it to you. This one is 3313. Here it comes. A 1 amp current passes through a 10 millihenry inductor coil. What is the potential difference induced across the coil if the current drops to 0 in 5 microseconds? I'll read that again. A 1 amp current passes through a 10 millihenry inductor coil. So I is equal to 1.0 amps. L is equal to 10 millihenries.
10 millihenries.
What did I say before?
I don't know, I just heard something different.
Oh, okay.
I just know.
What potential difference, so they want to know delta V, is induced across the coil if the current drops to 0 in a time of 5 microseconds?
Is Rachel's box your late pass receptacle now?
I'm blaming him.
Millihenry microphone is millihenry.
Milla. I mentioned that capacitors and inductors were kind of similar in a few ways. We've been writing down some ways. What is the purpose of a capacitor? I asked you before, but I need to just kind of reiterate this. What are we doing?
Store charge.
Storing charge, which stores what, really? Energy, right? You're storing energy. So in a capacitor, we're going to write this down on our little chart because we can, okay? In a capacitor, we store energy. What? Oh, you can't see.
I mean, it's interesting.
There's some dots, and that's fun. I'm sorry.
I
All
wasn't born with ears.
right, here you go. All right, now Jack can see. He opened his eyes, and there it was. Stores energy in where? What does a capacitor? Where does the capacitor store the energy?
In the electric field.
In the electric field. Okay. An inductor also stores energy. It seems a little bit funny to me that an inductor stores energy, but let's figure out how it stores energy. We know, let's start from power, because power can get us somewhere close to energy. Power is equal to current times change in potential, right? Or current times voltage. So if we write this in terms of the things that we know for an inductor, we can say that the power, the electric power, okay, that is dissipated in a circuit, well, if we're talking about stored stuff, then we're going to put a negative sign in there because the circuit is going to lose energy, not lose, because it's not, but it's transferring energy into the inductor, is equal to, well, it's I times delta V, and delta V is L di dt. Is that okay? Again, it's negative because the energy per time, which is what power is, right, is being transferred to the inductor from the rest of the circuit. Okay? And that energy is stored in the magnetic field that is established. When a current runs through an inductor, we know that a magnetic field is established. We've said that. Okay? It takes energy to do that, and that energy is stored in the magnetic field. We can then quantify how much energy is actually stored. The change in energy per time. Oh, that's just power. That's the opposite of power, I should say. So that's going to be plus.
Wait, what's that next to? Is that a subscript next to?
Subscript L.
Oh, okay.
Yeah,
Okay.
for the inductance, the inductor.
Oh, U. Yeah, gotcha.
So U is the energy,
Yeah.
right? L is the
Yeah,
inductor.
sorry, kinda
Yeah.
zoned
No,
out.
it's okay. It's been a bit, and it's a Thursday. You know, these things happen.
It's like Friday, not that Thursday.
I know, right?
It's the $3 Thursday.
Okay.
Multiply both sides by dt.
Let's multiply both sides by dt to get rid of the, to blah, blah, blah. And then we can integrate
Wait, why
to
is
get,
it-
what's that?
Wait, why is it positive?
Because the derivative of energy is the negative
oh.
of power, right?
Yeah,
So,
okay.
yeah. So if I integrate both sides, on the du side, that's just going to be u. Oops, I wanted an equal sign there first. Is equal to, well, the inductance isn't going to change, but it's the integral from 0 to I, because we're integrating I di. Is that an okay statement for all of you? So the current, again, in order to store electricity, store energy in an inductor, we have to have a change in current, right? And so we're changing the current from nothing to something. And we're going to integrate that. And if you integrate I di, what do you get? I squared over 2, or 1/2 I squared. And I'm going to put that L in front of that because it still exists. So you've got UL is equal to 1/2 Li squared. And we're going to write that down on our sheet, on our little chart, because that's interesting. We're going to say stores energy in the magnetic field. And if we quantify the energy stored, bless you again.
Thank you.
I swear if you do it one more time.
I'll say bless you again. 1/2 Li squared, which is, eerily similar to,
Everything else.
right?
1/2.
C delta V squared. 1/2 Kx squared. 1/2 MV squared. Oh my gosh. Well, that's nice. At least it looks the same.
Except what letters
What's
you
the
use,
potential
I don't
energy
know.
of electric field 1/2?
Well, we know the thing in general.
Say what now?
Yeah, it's
What's
something
electric
that's-
potential energy?
Just in general?
Like what? Now, how do you quantify it?
You have a 1 in 20.
It depends on what you're, like if you're talking about just a uniform electric field, if it's like a, from
Pick a
charges.
kinetics equation.
In a uniform electric
Yeah,
field.
definitely it.
Obviously.
U is equal to E times
ED.
D, right? Yeah, that's what's in my head. All right,
Yeah, can you scroll up like one, go back to that chart, just scroll up one, I just wanna make sure.
scroll up to the chart. Are we okay?
I'm good, yeah.
Okay, sweet. All right. What else was I going to say here? Because they like to do algebra. That's as far as I can tell where this next little step came from. Let's do some algebra. Let's write, because we can, the energy stored in the inductor in terms of the magnetic field. You ready? Here it comes. It's going to be fun. Not really, but we'll try it. U sub L is equal to, so it's going to be 1/2.
You don't even say it's going to be fun.
No, it's not fun.
No, it's not bad. It's just I just think it's funny mostly. Instead of L, I'm going to write it in terms of that magnetic field stuff. So that was mu naught N squared A over L times I squared. So that's all I did. I just plugged in the statement that is L. So that's getting it kind of in terms of magnetic field. Like there's that magnetic fieldy stuff in there. And then, this is what we're going to do. I said I wanted it in terms of magnetic field. So let's remind ourselves of what a magnetic field is. That was the, what was it? Mu naught N I over L, right? So now we want to get from this thing that has a whole lot of the same stuff in it to this thing. You see what I'm saying? Like they're very similar looking.
Wait, what's that again?
This is a magnetic field of a solenoid.
Okay.
Is that okay?
Yeah.
Magnetic field established for the solenoid. So I said that I wanted to write this thing in terms of that. So I need this. I need to get from here to there.
You already have the
Either
individual
square
eyes.
that-
I have an N and I have an I, but what do you notice about the N and the I on the left-hand side? They're squared, so probably we're going to have to square this whole mess. If we do that, we're going to have to get some other things, right?
Just gotta go to the store, gotta pick something up.
Got to pick some stuff up. So we're going to have a 1/2, I think, right? I need an extra mu naught on top, which means that I also have to get a mu naught on the bottom.
Yes, they did my thoughts exactly. L of
The N is okay. There's an L on the bottom here, and I need how many L's on the bottom over here?
1. Well, 2.
Well, it's squared, so that means I need to get an extra one. If I need an L on the bottom, I also have to get L on the top. And am I good besides that? Was it just those two things that I
And
needed?
there's an A.
And there's an A. Is that okay? So then I can write this U sub L. So again, the energy that's stored in that inductor is equal to, I'm going to write this as 1 over 2 mu naught L times A times, what is this thing then? B squared. And then they're going to take it one step further. I don't know if you remember, I feel like the capacitor stuff we did was forever ago. When we were defining capacitors, one of the things that we did was to define what we called the energy density of an electric field. Do you remember doing that?
Yeah.
We did. I looked back and it happened. So let's write it down. So the energy density.
Oh, that was rho. Yeah, okay. Right. No. It was J.
It was the fucking.
I'm just throwing out letters now.
I'm gathering.
Keep going.
Energy density is little u sub E, and it was equal to 1/2 epsilon naught E squared. Energy density is defined as, I'll go right back to that in just a second.
Potential energy per volume.
Energy per volume. What is L times A?
Volume.
Volume. So the energy density of a magnetic field is 1 over 2 mu naught B squared. Question, Andrew?
So, density times volume equals.
Yes. Is that okay? So now I'm going to bounce back. I know I keep bouncing forward and backward, and I'm not trying to freak you out. I'm just wanting to write this down. I'm so mean. I know. It's not exactly the same, but it's very similar, right? There's a lot of similarities up and down that list there.
Oh, wait.
They both have those weird little constants, right? Weird little constants. All right. Let's do one more problem.
Or is it an exercise?
It actually is labeled example.
There we go. It's not a problem. It's an example.
I have a problem for you. No, I don't. I have an example for you.
She has a problem with me.
That may be true. All right. The 10 microhenry inductor that we had in the first example,
Which number is this?
3314. 10 microhenry inductor, the same one we had before, was how long? Do you remember?
5.7 centimeters.
Oh, you guys have such good memories. And it had a diameter of what?
4
Or
millimeters.
what?
Millimeters.
Millimeters. Yeah. Suppose it carries a 100 milliamp current. What is the energy stored in the inductor? What is the magnetic energy density? And what is the magnetic field strength? They want to know 3 things. So it's really 3 exercises for you, Jack.
Okay, hold up. What was it?
I'm going to tell you. I want to know the energy stored in the inductor. I want to know the magnetic energy density. And I want to know the magnetic field strength. Oh, you can't see that though. There you go. Do it. Like this one?
Yeah, I don't have.
Don't worry.
Okay.
Oh.
All right. It's time. I hope you have a wonderful weekend. I'll see you on Monday. So, what's that? No, I was just thinking and I was trying to make sure I was right. So Monday.